Thank you. I must thank the organizers for getting us back on track after a very long 2 years. Uh, okay, so I will be talking about intermediate spectral statistics of a particular kind of random matrix ensemble, that is the beta ensemble. I will explain how that is constructed. So this work is done with a very hardworking student of mine, Adhay, at ISAR Kolkata. So before we start, let's go back to a dynamical systems, namely a classical kicked rotor. And we know if the kicking strength increases, dynamics changes from that of integrable to complete chaos. And you see there are a range of intermediate values of K for which we get intermediate dynamics. By intermediate dynamics, I mean there are integrable islands embedded in sea of chaos. The question that we ask is that what is the corresponding picture that emerges if this is a quantum system? So way to study that thing is that if we consider a quantum kicked rotor, for which if I take this Hamiltonian, let's take it in some truncated basis as some matrix, which we can diagonalize. We study its eigenvalue properties. And yesterday Shubhro gave us some background of this various kind of matrix ensembles. So depending on the symmetries you have in the Hamiltonian, you can have this eigenvalue distribution which is parameterized by some beta. And beta in this case can take 1, 2, 4, depending on whether you have orthogonal, unitary, or symplectic symmetries. So on the one side, we have integrable dynamics or classically integrable dynamics, whose corresponding quantum version will show the Poisson statistics, that is beta going to zero limit. That means that all the energies are clustered together. There is level clustering. And if we check for the eigenfunction properties, and they can have some localization or non-ergodic behavior. On the other hand, we have these classically chaotic systems whose corresponding quantum version will have some eigenvalue distributions given by this kind of form, with beta taking some integer values. So that means the levels are repelled. No two levels can come arbitrarily close to each other. And if I look for the eigenfunctions, this will be extended states or this will be ergodic. Okay, so with this crash course on quantum chaos, so if we now see what do we mean by intermediate statistics. So if I go for the Wigner-Dyson ensemble, this beta is also called the Dyson index. So these are primarily random matrices, symmetric, and the variance of the off-diagonal elements are very restricted because the beta values can only take very special values. The generalization of this kind of ensemble came as soon as this was proposed in 1959. So almost about a year later only, people started thinking of generalization of this kind of matrix ensemble. And the first was that you can take this off-diagonal or the diagonal variances to be any numbers. And as you vary the ratios, you can go reproduce various kinds of intermediate statistics. Then there is another kind of generation. One can think that, okay, don't consider a full matrix, rather consider banded matrix. That's a more physical situation where the interaction dies after a certain scale. And these are called the random banded matrix, which is also very well studied in various contexts. And depending on what kind of function you take, whether you could take a power law cutoff or some exponential decay, various ensembles can be created. Of late, there is also popular way of generalizing these ensembles that you consider any H0, which can be integrable, chaotic, doesn't matter, some H0, which you pot up with by some another matrix, say V, and you construct what you call a deformed ensembles, and then also you can produce various kinds of intermediate statistics. And some of you might be familiar with this kind of ensemble, which is very popularly known as the Peshukas-Yukawa gas. So the beta ensemble is a slightly different in a special way. So let's go back to Wigner-Dyson ensemble, and which is a full matrix, random matrix, symmetric. And how do you tridiagonalize it? So if you go back to your computational courses in undergraduate, so what we learned is that you can trigonalize these matrices by successive Householder transformations. And okay, so no wonder we'll end up having a tridiagonal matrix. But what happens here, the diagonals are still some normal distributed random numbers, but the off-diagonal elements are drawn from some chi-square distribution. See, if I have a lattice picture, these are the on-site terms, these are the hopping terms, and the hopping interactions increases as I go along the lattice. Okay, so this is a very asymmetric kind of situation. And what the questions that we're asking is that if I take this matrices as some Hamiltonian of some system, okay, what will be the spectral properties in terms of these eigenvalues and the eigenfunctions, or whether they have some relevance in terms of physical quantities. one parameterization that I will do, I won't be talking about beta anymore. So I will represent beta as n to the power minus gamma, and I will vary this gamma. Okay, so first let's look for the short range correlations. Yesterday we also seen measures of this kind. So if you don't want to go through the hassle of unfolding the data, so you take the ratios of nearest neighbor spacings and you compute their distribution from which calculate the mean spacing distributions. It's a very well studied quantity, and in our case, as we vary this gamma from 0 to some minus some large number to very positive large positive number, there seems to be transition at some gamma equal to 1. Now, eigenvalue statistics itself doesn't tell you much about what is the type of the transition. That's only half of the picture. One has to go to the wave functions. So one is, if I look for the wave functions for various realizations, and whether I take two neighboring eigenvalues or eigenfunctions from the same realizations or different realizations, I compute what is known as the Renyi entropy. And this Renyi entropy, if there's two eigenfunctions of spreads equally over my lattice, over my system, so this is going to be very close to 1, which can be exactly calculated, this limit. And as we go away, as gamma increases, so this value diverges. So it shows that around gamma equal to ET, there is some transition, which is like an ergodic transition. Okay, so what transition that we are seeing here, even though we don't know what actually this transition means in general, so here we can identify that thing with some ergodic transition. So this is for the short range correlations. If you go, let's go for the long range correlations. That can be done in various ways. Don't look for nearest neighbor spacings, look for higher order statistics, or equivalently, you can also look for, take the fluctuations around some mean level, these deltas, take a Fourier, go to the Fourier domain, and it can show very limiting cases are very easily understood. If it is completely uncorrelated, it will be like a random noise. So this power spectrum will go like 1 by omega square. And if it's correlated, then it's like a pink noise, it will go like 1 over omega. In the intermediate state between 0 and 1, there is some critical frequency omega c, okay, which distinguishes the correlated and the independent part. Now, in the coming to the eigenfunction part, so one can study this localization properties, okay, which is done by the inverse participation ratio. With this measure also, we have seen many times in this conference. So if I take this wave function, raise it to power 4, and if this everything is localized, then this measure gives a value of 1. Okay, it's everything's like a delta function. And on that, if it's spread over the lattice, this number goes to 1 over n. Okay. So here I can identify this transition. There's another transition at gamma equal to 1. Okay, and that will be associating with the like an Anderson transition point. Now, these are the static properties coming from the eigenvalues and the eigenfunctions. One can also go to the do some dynamics. I mean, suppose this is a Hamiltonian describing some physical system, which describes some dynamics of some physical object. So let's take some wave function, time evolve it, take its overlap. One can calculate the survival probability. What I want to show here is that in the limit that when it's in the ergodic regime, one can find some correlation hole, one can find the time scales and find the correlation hole, which is a telltale signature that there is going to be some ergodic property. Okay, so let's try to see, put everything together. So this is our gamma axis, this is our beta axis. On the left hand side, we have repulsion or the ergodic behavior. On the right side, we have clustering or the uncorrelated or localized behavior. And in the intermediate region between 0 to 1, we have this intermediate statistics, which is called non-ergodic extended states. Let's see how we can, so these are very, if you're coming from the dynamical system background, this is very, some of you might remember this type of plot is like a recurrence plot. So I take two wave functions, I compute the covariance. If it's I equal to j, this is going to be 1. If it's completely random vectors, this is 2 by pi, which can be exactly calculated if it's ergodic. And if it's localized, then if I go along any such line for row constant or column constant, I won't encounter any other such objects because it's localized, it's just pinned at one side, it doesn't interact with anybody else. Okay, so this, if I order my sites according to the localization centers, then all these points will be localized because here in the initial the lattice is the on-site terms are very dominant. As I go further along this lattice, the localization length spreads. I can draw an equivalent picture if I order it by the energies. So this is a very nice system for which we get very non-trivial localization properties in some and extended ergodic states. So that makes us ready and try to see if this system is any good for a physical system like a spin chain. Initially, it was quite nice. So we can map this, and if I take some disorder strength, I can find a one-to-one mapping with these beta values, which was nice. But then there was frustrations because the higher order statistics doesn't match. One proposed some measures like a beta chain sample, but that's a different kind of story for another day. Okay, so these are the main conclusions. You can find all the details in the references, and these are some ongoing work. And I conclude by thanking you. And Raka already said that we are that is coming up. Hope to see you there.
So do you have any questions?
Yes.
So how do you map from this beta to that spin chain? Can you tell?
No, we don't just numerically. So we diagnose the either of them, and we can find some distribution, and then we try to do a parameter fit and find the
see.
corresponding beta.
You find different kinds of beta there. Like when you
For each W corresponds to a beta. For nearest neighbor, there's a 1-to-N mapping. But if I expect the same thing for a second nearest neighbor, it doesn't happen. It happens for different beta. So it's not a good model in that sense.
Any more questions?
Yes, yes.
So you mapped from the like fully random matrix to this tridiagonal thing, and so there you said that the diagonals are just normal,
Normal distribution.
and the off diagonals are
I-square distribution.
chi, and they vary along the chain. Is it?
Yes, the scale factor, the chi parameter varies according to the lattice index. Yes,
So it's like an electric field.
it's like an yes.
Okay, but and then you get localized at different.
So what happens? The localization, the initial sites are strongly localized because they are the diagonal elements are very strong. And as I go along, the off diagonals become strong. So it's an inhomogeneous localization. There the correlation length increases.
But is it exactly equivalent to just putting an electric field in a disordered thing, or?
Not exactly, because all sides don't see the same field. It's more like putting like a tilt. Like a yeah.
So I'm saying like if electric field would be like a linear potential.
No, it's not a linear.
It's not a linear.
Linear potential.
Do you have any more questions? No. Okay, so we can thank the speakers.